Okay, guys, welcome to the final exam review. This is just the final from the last semester, so we'll kind of go through how to do this, and hopefully you get a better idea of like what you're going to be asked and kind of how to show it. This first page is, well, I mean, the only question I see is your name, and that hopefully you know that one. If not, definitely need to study that. We'll just go on to the next part. Okay, so each of these are worth 2 points. It wants us to record your answers in the space provided on page 4. I don't know what page this is. This is page 3, so it'll be on the next one. We'll just write them on here. But this first question says, the table below gives selected values for the differential function f. In which of the following intervals must there be a value c such that f prime of c is 1/2? Well, this question, or this is trying what you use, is your mean value theorem. And the idea is, if you know that the slope from a to b is 1/2, then there must be somewhere in the middle that the slope is that has the same slope, right? So what we're going to do for each of these intervals, we're going to find the slope between them, and we'll see for which one do we have a slope of 1/2, because that's going to guarantee that there's somewhere inside the interval that is going to have the same slope. So for the first one, from 0 to 2, well, our slope is just, like f of 2 minus f of 0, 2 minus 0. I won't write that out every time, just so you see it at least once. So minus 6 plus 3, because minus 3, over 2, minus 3 over 2, not 1/2, so it's not going to be that one. From 3 to 5, I'll put it over here. My f value at 5 is 4, 0, 5 minus 2, 5 minus 3. 4 over 2, which is 2. It's not that one. From 5 to 8, well, it's going to be 1 minus 4 over 3 minus 5, 8 minus 5, which is going to be minus 3 over 3, which is negative 1, not 1/2. From 8 to 10, I'll go down here. It's going to be 2 minus 1 over 10 minus 8, which is 1/2. Well, that one works, so that's going to be true for that one. Just for the sake of completeness, let's check this next one. It's going to be 6 minus 8 over 15 minus 11, minus 2 over 4, which is negative 1/2. So it's negative, that doesn't work. If it's positive 1/2, it would be. So this one is just D. In the side note, the reason why I knew it was mean value theorem is asking me about a value inside an interval, such as the derivative equals a certain thing. That's pretty close to what the mean value theorem says. For this next one, it gives us this expression. It's a Riemann sum approximation of which of the following integrals. Well, our general format of a Riemann sum is it's going to be from k equals 1 to n, where that n is the number of rectangles or divisions. This sum means we're adding up all the rectangles, and each of them are going to look like f of a plus k delta x, where delta x is the width of each one, times delta x. We also know that b minus a over n equals delta x. So the first thing I can tell from this is that that's our delta x, that is our n, and right here is our a. So just from that, just those 3 pieces alone, well, I can knock off a, b, and c. Well, why? Because a is the lower bound of our integral. This is how you approximate the integral from a to b. So this a value has to be our lower bound. Okay. Well, just to explain where this 11 comes from up top, what we could have also done is, b minus a over n is delta x. So that means that b minus 5 over 30 is 1/5. And then you could figure out b is 6 plus, sorry, I was going too fast there. B minus 5 would be 6, so b would be 11. So you can figure it that way. But the real difference between these two, also you can figure out the function's x to the 7th y, because all of this stuff matches with this stuff, and this is to the 7th, so that means your f function would have been something to the 7th power. The difference is that 1/5. Well, what does the 1/5 represent? Well, that represents where we make our curve we have all these rectangles, how wide each of these are. So our delta x, which is 1/5. But when we actually do the integral, we're just shading in, right? We're not going to multiply by the width of our rectangles because we're not using any. So that's wrong because in the integral, you don't have to include the 1/5. So that means D is the only correct answer. For this next one, wants us to evaluate the limit as h goes to 0 of cosine of pi over 2 plus h minus cosine of pi over 2 over h. There's kind of two ways we can do this. We could use a L'Hopital's rule because the top goes to 0, the bottom goes to 0. You can take your derivatives. Derivative of cosine is negative sine pi over 2 plus h. And then derivative of cosine pi over 2, that's just, cosine pi over 2 is just a number, so that goes away. Oh, oops. And then the bottom, derivative of the bottom, which should just be 1, and you reevaluate, and you're going to get, as h goes to 0, you get negative sine of pi over 2, which is negative 1. You could do it that way, and that negative 1 is our answer. The other way that you could do it is this is the definition of a derivative, which is limit as h goes to 0 of f of x plus h minus f of x over h. That's the same thing as f prime at that x value. So our function here is cosine, and the x value we're looking at is that. So if f of x is cosine, derivative of cosine is negative sine. And if we're evaluating that at pi over 2, we get negative sine of pi over 2, which is, as we just showed, negative 1. So negative 1 is the answer there. Continuing on, suppose we're given this integral, and from 2 to 4, f of x equals 10, and from 2 to 4, g of x is negative 5, which the following expressions cannot be determined. Well, from 4 to 2, well, if we just flip our bounds, all that does is that will give us the negative version of them, so it would be negative 10, so it's not that one. G of x over f of x, that's going to be the answer here. You can't divide two integrals. That's not how that works. It's just a property of integrals. But let's just say you didn't realize that was the answer. Well, let's just go ahead and we can show that you can do the other ones. If you have a constant, you can move that outside. So 7 times integral of 2 to 4 of g of x dx, which we know. So that's minus 35. For this one, you can your integral is linear. So if you have two things add together in your integral, you can break it into two different integrals. That's what the linear thing means. Then you can move the 5 out front. You can evaluate that one. And the other thing is, integral from 2 to 3 and 3 to 4, well, we can just combine that into 1 from 2 to 4. And we know that one. So you can find all of these but B. So the answer there is going to be B. Last one is consider the function f defined by f of x equals 3x squared minus 4 when x is less than 1, and 2 when x is 1, and 6x minus 4 when x is bigger than 1. Our questions are, which of the following are true statements about this function? The limit as x approaches 1, the limit as x approaches 1 of f of x exists, f of 1 exists, f is continuous at x equals 1. Well, the limit existing means that from the left side and the right side, they're going to equal. And so from the left side, when x is less than 1, we're going to have this equation. From the right side, we're going to have this equation. So as we plug in numbers closer and closer to 1 on each side of those, am I getting the same value? So if I think about, just for the sake of getting close, let's just say that we're just going to evaluate this at 1. Technically, we can't, because if it equals 1, we're here. But just to see what this value is approaching, I'll check it at 1. So it'll be 3 minus 4, so we get negative 1. Okay, well, let's check about this one at 1. So 6 times 1 minus 4 would be 6 minus 4, which is 2. Those do not match, so the limit does not exist. So that means that anything involving number 1 is wrong. So now we're between 2 and 3. Well, for 2, f of 1 exists. Well, For when x equals 1, it's 2, so that definitely exists, because you can plug in 1 and you'll get something out, so that works. Fortunately, that doesn't rule out any of the remaining 2. So it's continuous at x equals 1. Well, it'll be continuous if the limit exists and it equals the function, right? You know, if it looks all nice and smooth, where like the limit matches on each side, and they both go to what f of 1 is, then that works. But issue is this will look continuous from the right side, but from the left side, it's going to be something different. So this one is not true. Therefore, the answer is C. And then down here is just a place where we could write our answers. I guess this was what B, C, and going back to the previous ones, those were D, D, and C as well. And that's it for this section. Going to the next one. Evaluate the following limits, or say that they do not exist. Use infinity, minus infinity if appropriate. We need to justify our answers, which, I mean, we'll go through that. And if we use L'Hopital's, just to clearly justify why you were able to do so. Okay, so this first one, if I were to try to evaluate this, I'm going to get 0 over 0, because its limit as x approaches 8 of x cubed minus 64x over x minus 8. So, because it's 0 over 0, we use the L'Hopital's. You don't have to put the little thing over the O. I'm just extra. So when we do our L'Hopital's, we're going to take the derivative of the top, so 3x squared minus 64. And the derivative of the bottom, which is just going to make this 1. And now when we reevaluate, we're going to get 3 times 64. Sorry, 3 times 8 squared, which is going to be 64. Minus 64, so that's going to be 3 times 64 minus 64. You plug that in a calculator, you'll get that's 128. Okay, for this next one, limit as x approaches 0, well, that's going to be like sine of 0 over e to the 0. Well, e to the 0 is 1, and sine of 0 is 0. So that one's just 0. We don't even need L'Hopital's rule. You can just take the limit straight up. Okay. Next, we need to calculate the following derivatives. You do not need to simplify, so we don't have to worry about like having to reduce things. So it gives us this g function. Well, the derivative of any b to the x is just going to be the natural log of that base times that b to the x. So derivative of 4 to the x would be natural log of 4 times 4 to the x. And then derivatives, if you have multiple things added together, you can just do them all separately and add each of their individual derivatives together. Derivative of x to the fourth, that's just a power rule, so bring down the 4, reduce the power by 1. And derivative of 4 over x, well, I'm going to write this as 4x to the negative 1, because I like to use power rule, I don't have to use like a quotient rule here. So if I bring down the power, it's going to make the plus I just put there into a minus 4x, and we drop 1 to the power, so x to the negative 2. And I don't have to simplify, so if I just put g prime of x to say like what that is, that's my final answer. Next, it wants f to be arctan of x. Find the second derivative of f. If you don't know derivative of arctan, usually they'll give you like a formula sheet at the end, so it'll be on there. But f prime of x is going to be 1 over 1 plus x squared. So for this, we could use quotient rule, and that's going to be totally fine. You could also write this as like 1 plus, sorry, it was a bad plus, x squared to the negative 1, and then just do like a power rule and a chain rule. Either one works. I'll go ahead and do the quotient rule, then I'll do the other one to show that they're the same. So we do quotient rule. Well, quotient rule is if you have an f over g, it'll be f prime g minus g prime f over g squared. So it will be f prime derivative of the top. Well, derivative of 1 is 0 times 1 plus x squared. Minus derivative of the bottom. Well, that's going to be 2x times 1. And then on bottom is 1 plus x squared. So those get minus 2x over 1 plus x squared. If we were to do it this way, well, we bring the negative down, 1 plus x squared, now to the minus 2, and derivative of the inside is 2x. We're going to try to simplify that, minus 2x over 1 plus x squared squared. So either way, that works, just as long as we have this, or something equivalent, like we don't have to simplify everything all the way. And that's it for that page.